All right, let's jump straight into this explainer. Today, we're unpacking one of the absolute wildest engineering marvels in human history. We're going to look at exactly how naval architects managed to construct a massive, self-sustaining airport that operates on a constantly heaving, twisting ocean. We usually just think of these things as military assets, but from a pure engineering standpoint, they're essentially highly complex, moving islands. We're going to dig right into the physics, the structural design, and the insane electromagnetism that actually make modern naval aviation possible. To figure out how this entire system of systems works, we're going to hit 5 key areas. First, the ultimate moving island. 2, engineering the double bottom. 3, the angled deck revolution. 4, emails and electromagnetic launch dynamics. And finally, number 5, the art of the arrest. Think about this fundamental problem for a second. A normal land base is completely static, right? You pour some concrete and it just stays perfectly flat. But a carrier? It has to maintain extreme structural integrity, what engineers call its tolerance factor, while heaving around in 20-foot open ocean swells. The runway is literally twisting and bending, while highly sensitive jets are trying to land at blistering speeds. How on earth do you stop the ship from just tearing itself apart?
Well, that brings us to Section 1, the ultimate moving island and surviving the open ocean.
Because we don't have the luxury of a 2-mile concrete runway out there, modern carriers use something called the K-bar system. You're dealing with a heavily restricted flight deck, so K-bar uses massive external energy to literally throw the aircraft into the sky and equally massive energy absorption to snatch it right back out of the air. It basically turns a pitching 200-yard runway into a high-throughput, continuous flow assembly line. Just think about the sheer peril described in historical naval records from ships like the HMS Ocean. Carriers often have to steam at maximum speeds, around 25 knots, directly into the wind, just to generate enough wind speed over the deck for lift. So imagine this massive steel structure, violently pitching and rolling through heavy waves at 25 knots, all while you're trying to execute perfectly calibrated landing ops. It elevates the flight deck into an absolute masterpiece of stress and strain calculation. Which leads us perfectly into Section 2, engineering the double bottom. Let's look at the science of buoyancy and survival. So, according to some incredibly strict naval classification rules from Bureau Veritas, a carrier's inner bottom has to be at least 760 millimeters above the keel, extending outward to protect the turn of the bilge. This is the famous double bottom. They don't just build one big hollow boat. Instead, engineers chunk the lower hull up into thousands of small, steel-sealed rooms. Because of this honeycomb compartmentalization, if the hull gets breached, only a tiny, localized section floods. It preserves the ship's buoyancy and makes it incredibly hard to sink. And this is exactly why the flight deck itself has to act as a core structural member of the ship, a design they actually pioneered back on the Forrestal class. The deck isn't just a roof, it's the main strength deck holding the whole shebang together. It has to support these intense structural singularities, like massive cutouts for catapult tracks, deflector hinges, and arresting gear units, while fighting against continuous, twisting wave hull girder loads inflicted by the ocean. Balancing those localized impact forces against the bending of the entire ship's spine requires some truly staggering math. Now for Section 3, the angled deck revolution, unclogging the runway. The catalyst for this massive design revolution was simply weight. As jets got heavier and faster into the 1950s, hitting weights like the 75,000-pound A3 heavy attack jets on the USS Forrestal, the old straight deck designs were basically obsolete. They just couldn't handle the physical realities of recovery anymore. The speeds were way too high and the kinetic energy was just too massive. Something absolutely had to give. Enter the angled deck, which shifted everything from a terrifyingly high-risk straight path to a remarkably elegant solution. On a straight deck, if a pilot missed the arresting wires, they were barreling straight into steel cable emergency barriers, or worse, parked aircraft. But by pointing the runway slightly to port, a missed landing, what they call a bolter, just becomes a safe fly-around right over the open water. It completely unclogged the runway, letting them safely launch and recover jets at the exact same time. Moving right along to Section 4, EMALS and electromagnetic launch dynamics. Going from steam to linear induction. To actually get those heavy jets off the angled deck, engineers now use EMALS, or the Electromagnetic Aircraft Launch System. For decades, carriers relied on steam catapults, which were heavy, complex, and a nightmare to maintain. EMALS chucks the steam and uses an advanced alternating current linear motor system, specifically a permanent magnet linear synchronous motor.
It fundamentally rewrites how energy is stored and conditioned to get a massive plane airborne.
If you're wondering how linear induction works, just picture a standard electric motor, but unrolled and laid completely flat on the ground. Instead of spinning a circular shaft, AC power energizes a slotted stator running right down the catapult track. These electromagnetic forces interact with permanent magnets on the shuttle, basically pulling the aircraft forward. It gives you insanely smooth acceleration and can handle a much wider range of launch energies with way less mechanical wear and tear on the jet's airframe.
The real engineering magic happening inside those magnets comes down to a quasi-Hallback magnetic topology. In a traditional motor, you get thrust ripple, which causes a really jerky, uneven acceleration. But by combining a quasi-Hallback array with a parallel magnetic circuit, engineers can max out the raw thrust force while practically eliminating those dangerous thrust ripples, getting them down to as low as 1%. This guarantees a buttery smooth launch for both the pilot and the plane.
Finally, Section 5, the art of the arrest, catching a jet on a broad.
This is where the arresting gear steps up. Hiding below the deck is an absolute monster of a system made up of hydraulic engines and wire pulleys. When a jet's tailhook catches a tension steel cable on the deck, that hydraulic machinery instantly starts eating up the aircraft's massive kinetic energy. The pilot and the jet stream get hit with a crushing 3G deceleration force, going from flight speed to a dead stop in just 150 feet. If that force were even slightly higher, the hook would get ripped clean out of the chassis. It is quite literally a perfectly calculated violent collision. Now, all of this mind-blowing machinery, the compartmentalized double bottom, the linear induction motors, the hydraulic arresting wires, it all serves one ultimate metric, the sortie rate. That's simply how many precise missions a carrier can launch and recover over its deployment lifecycle. Because a carrier is a true system of systems, the reliability of every single tiny component dictates whether the ship is actually out there projecting power, running training ops, or just stuck in a shipyard for complex maintenance. And that really puts the incredible scale of naval architecture into perspective. When you take a step back and look at all these elements working perfectly in sync against the raw power of the open ocean, it redefines what a ship even is. It's not just a weapon. It's thousands of steel-sealed rooms, unrolled electric motors, and hydraulic engines catching jets out of the sky. It really leaves you wondering, just how far can human engineering push the absolute limits of physics before the ocean pushes back? Next time you see a carrier on the horizon, remember, you aren't just looking at a boat. You're looking at a mobile, engineered city.